Sollte, glaube ich, okay sein. Sonst, ja, mal probieren. Das Ding ist bloß, dass mein Wort auf der anderen Seite ist. Aber es ist lang genug. Ja.
Yeah, you keep the spark with slightly flat.
I kind of feel like getting started and not waiting. I suppose there's just this one microphone, so I'm going to awkwardly stand next to you to open the session. We'll go from there. Hi, everybody. Welcome to this session about synthesis for architectures and stuff. There are 4 really cool talks that I am excited for. This first one is about the port mapping performance problem on CPUs. And our speaker is Fabian Ritter, who's a PhD candidate at Saarland University. Please go for it.
Thanks for the introduction. And yeah, hi everyone. Welcome to my talk on our latest research on port mapping inference. So let's begin with a look at CPU architectures. Early processors followed a pipeline design like this. Instructions were fetched and sent through the processor stages to execute them one after the other. Natural question to ask is how can we use our processors efficiently? For such a traditional design, the key point is to arrange instructions such that no data dependencies cause resources to idle, ensuring the full pipeline. Nowadays, processors have grown a lot more complex than that. A key difference to the earlier design is that instructions are no longer executed strictly in program order. Instead, they're decoded into so-called micro-ops that are then handed to a scheduler inside the processor. The scheduler distributes the micro-ops among execution units that are grouped behind so-called ports. Each port can execute one operation at a time, but not all ports can execute all kinds of operations. In such an architecture, where instructions can be executed out of order, achieving peak performance becomes more complicated. Besides avoiding stalls from dependent instructions, we have another challenge. We need to give the processor instructions that can be executed in parallel. And therefore, we need to know for which instructions this is actually possible. This is characterized by what we call a port mapping. That is a mapping from instructions to the micro-ops that they decoded into, and from micro-ops to the ports on which they can be executed. These inner workings of processors are often only sparsely documented, if at all. This lack of information motivates our research. We want to infer a processor's port mapping that explains the performance characteristics that we can see when we run code on the processor. Since we cannot look into the hardware itself, we need to base our work on micro benchmarks. Prior approaches in this category or in this space fall into two categories. On one side, approaches like UOPS.info use hardware performance counters to count the micro-ops that each individual port executes. This enables micro-benchmarks that are straightforward to interpret and validate. However, some microarchitectures like AMD's Zen series do not have these performance counters. So therefore, there is this second group of approaches that avoids performance counters and relies only on instruction throughput measurements. These works, however, come with other downsides. They are less suitable for validating the inferred port mapping, or they some of them even actually don't really produce port mappings, but just similar resource models that don't really fit into the typical port mapping model. Our work here brings together the best of both worlds. We follow the high-level structure of the UOPS.info algorithm to obtain actually an explainable port mapping that can easily be validated by hand. But we modify it to work without per port performance counters, so that's actually applicable to more microarchitectures. So let's have a look at this high-level algorithm first. The key notion of this algorithm is that of blocking instructions. Blocking instructions are instructions that are each executed as a single micro-op. The idea is that in a micro-benchmark, we can reliably flood all ports that can execute this micro-op by issuing enough of the corresponding blocking instructions. In this example port mapping here, we have 3 blocking instructions: mul blocks port 2, store blocks port 3, and add blocks ports 1 and 2 together. FMA is not a blocking instruction since here it's implemented with 2 U1 micro-ops and 1 U2 micro-op. The algorithm assumes that each micro-op in the mapping has a corresponding blocking instruction. So for each instruction I whose port usage we want to infer, such as FMA here, we run a sequence of micro-benchmarks with each blocking instruction. When we mix this instruction I with enough instances of the blocking instruction, the associated ports will be flooded with their micro-ops. Therefore, every micro-op of I that can execute on any other port will do so. This means that by counting the additional micro-ops that still execute on the blocked ports besides the micro-ops of the blocking instructions, we can find out how many of the micro-ops of the instruction I map to some subset of these blocked ports. In our example, one micro-op of FMA cannot evade the flood of mul blocking instructions for port 2, while all its micro-ops can evade port 3. All 3 micro-ops of I cannot evade ports 1 and 2 when they're flooded by add instructions. Lastly, we subtract from each of these counts that we've observed the micro-ops that we already mapped to smaller port subsets. In the example, there is no smaller port subset for port 2, therefore one micro-op of the FMA instruction executes only on port 2. Of the 3 micro-ops we observed on ports 1 and 2, one is explained by the micro-op we already found, meaning that only 2 of I's micro-ops map to both ports 1 and 2. And we find that actually the counts that we get at the bottom do coincide with what our example port mapping gives. So in this original UOPS.info algorithm, the per port performance counters are used in 2 of these steps. First, they make it easy to identify and characterize blocking instructions. Second, per port performance counters allow us to count the micro-ops on a blocked ports. What we do in our work here is that we develop methods to perform these steps without per port performance counters. This allows us to adapt the original algorithm to previously unsupported microarchitectures. So for the first of these steps, to characterize blocking instructions, we use a counterexample guided algorithm inspired by approaches like CGAR or CGIS that you might have heard of. The algorithm keeps a set S of micro-benchmarks with measured throughputs. Initially, this set S may be empty or contain some pre-selected set of benchmarks. Then, in each iteration of the algorithm, we first search for a port mapping M1 that explains the throughput of all benchmarks in S. If the processor operates according to a port mapping, we can always find such a mapping. Next, we search for a different port mapping M2 that also explains the throughput of all benchmarks in S, and additionally, another benchmark E that distinguishes M1 and M2. That means these 2 port mappings that we found should agree on all throughputs that we have in the benchmark set S, but they should disagree on the one of the newly found benchmark E. If there is no such mapping M2 with distinguishing microbenchmarks, we know that it's indistinguishable by throughput observations from the processor's actual port mapping, which means that we're done because we found the right one. Otherwise, we can just measure the throughput of this newly found experiment E and just add it to the set and start on with the next iteration. Both of these mapping finding steps we implement with an SMT solver based on a formal model that allows us to connect the throughput of the benchmarks to the port mapping in there, which allows us to basically extract the port mapping that we found from the solution of the SMT problem. Now you might notice that this is actually already a fully fledged port mapping inference algorithm by itself, but we're only using it as a subcomponent of our approach. The reason for this is because due to the heavy use of the SMT solver, this counterexample guided algorithm does not scale to a complete instruction set architecture. We avoid this problem by restricting the instruction set to just plausible candidates that could be blocking instructions. So, for example, in the case study that I'm going to talk about later on, this means that we can just feed a dozen of instructions into the algorithm instead of 3,000, which makes a difference between hours and weeks to months of execution time, or probably even longer. For the other step that is problematic in the high-level or in the inference algorithm that we've seen, determining how many microbes cannot evade a set of blocked ports, we rely on properties of the steady-state port utilization during microbenchmarks. The idea is that by measuring the throughput of a microbenchmark, we can find out how many cycles the top utilized ports are occupied. If the microbenchmark consists mostly of blocking instructions of a kind, we know already that the most utilized ports are the blocked ports. So if we have an investigated instruction that we put together with a lot of blocking instructions, the microbes of the investigated instruction that can evade these block ports do not affect the number of cycles that we can observe at all, because they can evade to other ports. Microbes that cannot evade the block ports, however, do affect the observations. By measuring how much the microbenchmark is slowed down compared to a benchmark consisting only of blocking instructions, we can find out how many of the microbes are additionally executed in the block ports without actually counting these microbes, just by observing the throughput. So we used the algorithm with these adjustments in a case study on AMD's Zen+ microarchitecture. Since Zen+ does not have these performance counters for the executed microops on each individual port, the original UFZ-info algorithm is not applicable. Ours is, and the result is, to the best of our knowledge, the most comprehensive and accurate port mapping available for Zen+. We're not able to cover all the instructions because of some peculiarities about the hardware. But also these peculiarities are nonetheless interesting and insightful. So, for example, we found quite a number of undocumented or misdocumented hardware features of Zen+. For instance, we found that the timing behavior of general purpose store instructions does not match the official documentation. So there appears to be wrong. Another example is this group of vector instructions there. According to the documentation, they should all execute on the same two ports, but actually different bit widths and comparison predicates are executed differently. Lastly, we identified a set of hardware aspects that hinder our approach. Quite a few instructions, for example, do not execute ideally according to the port mapping model, often because of functional units that are not fully pipelined. These instructions are problematic for the counterexample guided algorithm and need to be filtered out. Another issue is the microcode sequencer, which is used for instructions with many microops because it reuses front-end throughput while active, which is also problematic for our benchmarks. Lastly, we evaluated our inferred port mapping by using it to predict the throughput of randomly generated dependency-free instruction sequences, and we compared the prediction accuracy to two prior approaches, PMEVO, an earlier work of ours, and PALMed. Our inferred port mapping achieves a better prediction accuracy with lower prediction error than either of them. These heat maps visualize this. Each instruction sequence is sorted into a bucket further to the top, the faster it is predicted, and further to the right, the faster it's actually executed on the hardware. Our data points are closer to the diagonal line, which means that the throughput predictions of our port mapping are more accurate. So to conclude, we investigated how instructions on modern CPUs are decoded into microops and how these can be executed on the processor's ports. Based our approach on an inference algorithm that originally relies on hardware-specific performance counters and eliminated that reliance. We used this counterexample guided algorithm that is quite helpful to characterize the blocking instructions. And lastly, the results of our work are, to the best of our knowledge, the most comprehensive and accurate port mapping for Zen Plus for the Zen Plus microarchitecture available. Thanks for your attention. I'm happy to take questions.
What's that questions? You can come to the microphone and say your name and affiliation before you ask a question.
I'm Matt from the University. I have two questions if I can. So number one, is this tool available somewhere, or maybe is there a plan or an opportunity to integrate this with the existing UX tool? It's a very useful tool where you can either look for the rest and get these if it doesn't have any sense.
So the our prototype implementation and our results, including the port mapping that we found, are available on GitHub and our artifact. We haven't integrated it yet in the Eureka workflow, but I did have because it's quite specific to x86 to Intel architectures internally. But some other work by them facile there, I did integrate it and have some promising results there.
My second question was about the hardware peculiarities that you said. I wanted to ask very specifically, if you could go back to that slide. Why is there a difference in BCNP greater than Q and BCNP greater than 5?
Apologies.
So what are the peculiarities here? Why are they so differently?
So I mean the thing is So the thing is, it's just that these different predicates and bit widths require. One can only execute on a single port, probably because it's more complex or less frequently used, and they just didn't include these functional units on more ports, whereas the other one is has more ports available. So that's just. Seems like it, yeah.
We're out of time. Thanks
Okay.
Thank you. That's great. Thanks. I am delighted for the next speaker to introduce Julian Oppermann, who now works at CodePlay Software on LLVM and MLIR and SYCL and AI compilers and all that stuff. This work from Julian was from his time when he was at TU Darmstadt, however. Please take it away.
Yes, thank you. So we all know that modern edge devices are expected to run complex workloads such as ML inference and signal processing algorithms. And in that context, ISA extensions, which I call ISACs here for short, are an energy efficient and cost-effective way to accelerate these demanding workloads on otherwise generic base cores. So in theory, the RISC-V ecosystem, which is modular and extensible, ISA would be ideal for this approach, but we observe that in practice, there's only limited reuse and exploration possible. This is due to the fact that on the one hand, implementing an extension manually is quite hard and requires intimate knowledge of the target architecture you're integrating it into. And all the existing solutions are vendor specific, so not really portable across cores and microarchitectures across one specific ecosystem. So our goal is to make ISACs design more accessible and portable. And to do so, we are proposing CoreDSL, a new user-friendly language to describe your ISAXs in, which is the input to Longnail, our microarchitecture agnostic high-level synthesis tool. To make this work, we rely on bidirectional communication with our Sky5 interface generator tool, which provides an HLS-friendly abstraction of the base course microarchitecture to Longnail and receives a tailored hardware module and a bit of metadata back from Longnail and is then able to integrate it automatically into the base core. So in other words, what the user would see is an end-to-end flow from this CoreDSL description down to an extended RISC-V core. So let's have a look at the language. As you can see here on the right-hand side, we've opted to use the familiar C-inspired syntax and augmented it with a couple of structural elements just to distinguish between behavior and other metadata required for such a description. One key feature of our language is that we are using a bit-width-aware type system, which has been designed to prevent an implicit loss of precision or sign info, which we believe is really important to enable safe and convenient interaction with narrow width integer values, which we believe is common in this ISAX use case. We are also supporting all the usual control flow constructs and even added a couple of ISAC-specific syntactic sugar. For example, Verilog style integer literals, a concatenation operator, and a range subscript operator. So CoreDSL would already be quite nice to describe simple R-type instructions, but we wanted to go beyond that. So we are proposing two novel language constructs in CoreDSL. The first one is the always block, which contains behavior that is executed continuously, independently of fetch instructions. The canonical example for that would be a zero overhead loop, which I have as an example here on the slide. And in general, always blocks are great for ISAXs that would usually require a separate functional unit to be designed. The other construct is the spawn block, which contains behavior that is executed in parallel to other instructions that are in the pipeline. And a canonical example for that would be just any long-running instruction, for example, a CORDIC-based square root computation, which is my second example in the lower right on the slide. Of course, just defining that in language doesn't cut it. We also have the hardware support for this construct, and it's provided by our extended Sky5 tool, which handles the data hazards and arbitration for us, provides access to the program counter, and even instantiates the custom registers that we define in our CoreDSL description. Then let's talk about Longnail, which is our high-level synthesis tool for ISAXs. And we built it from scratch on top of MLIR and Circuit. It follows the usual gradual lowering between dialects that basically all MLIR-based compilers do, and we are using a couple of upstream dialects and our own custom dialects in this lowering flow. So we have the CoreDSL dialect, which is an AST-like dialect, really close to what our custom front-end produces, contains instructions, always blocks, registers, and so on. Then this is lowered to the LIL representation, which is which you can think of as control flow graphs of combinational logic. Next step in our pipeline is the static scheduling phase, for which we defined a custom scheduling problem that targets Sky5 supported cores, and we also implemented a simple IRB-based scheduler for that. The scheduler respects the availability of the interfaces, which I will talk in more detail on the next slide, and its objective right now is to minimize the latency and lifetimes of intermediate results. After scheduling, we construct an ISAX module in circuits, dialects, and abstractions, and you also use circuits Verilog emitter to get our HDL description of the constructed microarchitecture. Now, the really novel and important bit in our approach is the bidirectional communication between Sky5 and Longnail, and I want to talk about that here now. So Sky5 exposes several sub-interfaces for common ISAX functionality, such as reading a register, writing a result, and so on. And these subinterfaces are available between an earliest and an optional latest time, which we represent as a number of cycles since the instruction has been fetched. This information is then collected into what we call the virtual data sheet for a specific core. So it's just a simple YAML-based text format. On the Longnail side, inside the LIL dialect, we model Sky5's subinterfaces as individual MLIR operations. And so when we put our LIL level description into the static scheduling phase, we just model the earliest and latest times that are coming from Sky5 as scheduling constraints. Invoking the scheduler on that then computes in which specific time step each interface is used, and this information is then handed back to Sky5 to provide the respective values and just to facilitate the integration at the right time. So this Sky5 configuration file that I'm showing on the bottom of the slide here, it contains this interface schedule and also additionally metadata such as the instruction name and the binary encoding mask of the instruction. For the evaluation, we wanted to show that we do have this end-to-end flow working. So we just collected a couple of sample ISXs to put through our flow. We have an auto-increment load store extension dot product that you saw earlier on the slide. We have an indirect jump, a bit of cryptography, the square root computation, and the zero overhead loops. That was the example for the always block. And these ISXs use the features of our system. So we are using custom registers here, main memory accesses here, program counter access here, using the for loop several times in our examples, using a spawn block, and finally using an always block. These ISXs are then integrated into 4 microcontroller class RISC-V cores with quite different microarchitectures, going from 0 to 5 stages. So we also have a FSM-based core in our setup. And as you can see by the area demand and achievable frequencies, these are quite different internally. We have implemented all this down to layout on a 22 nanometer commercial ASIC reference flow. So for the results, I unfortunately cannot show you our entire results table. I'm just picking one example here and would invite you to have a look in our paper for the complete set of results. First thing I want to point out here is that we can easily compose multiple ISXs together. So in this example here, I'm looking at the auto increment and zero overhead loop combination. For the area, we see the expected area increase here. That's okay because we are using additional hardware to achieve some form of acceleration. The frequency remains mostly unaffected and just fluctuates a bit up and down. I wanted to show a quick back of the envelope calculation here. Sorry. So we are looking at a simulation of summing n array elements and doing that on the baseline Beck's RISC-V core takes around 18 instructions per array element in the steady state. And using the extended core and of course adapting the program to that, we are executing at 11 instructions per array element. So in this case, 16% more area gave us 60% speed up by using the extended core. This work has been done in the context of the Scale4Edge ecosystem, and we already had embedded application engineers use our CoreDSL language to describe an ISAX for an audio event detection. It was quite successful, and they liked working with that. It even led to a successful tapeout of the system, even though using earlier versions of Sky5 and a handwritten ISAX module. And in that case, the results were even more impressive because 15% extra area led to a 2x speed up and led to this demonstrator reach real-time performance, which was not possible before. So to conclude, with CoreDSL, Longnail, and Scan5, powerful RISC-V ISAXs are now accessible to non-hardware engineers and portable across different microarchitectures. In the future, we plan to make them even more area efficient through intra and inter ISACs resource sharing, and we also want to look at larger and more complex cores in the future. And with that, let me thank you, and I'm happy to take questions. Thanks.
What was that question for Julian? Please say your name and career.
So when you add all these extensions, how do you make sure it's for RISC-V, it's not for other forms, right? So how precise the spec can be. And second of all, a lot of times people use based on human expertise and could design all these instruction extensions. Like, so I saw your result are pretty promising. Have you ever compared to human-based designs?
I'm going to start with the second question. So we don't really have compared ourselves with human-written designs, but we really do think to have this ISACs approach taking off, you have to have automation. Otherwise, you can't iterate on your designs really well. And so even though maybe a human designer, an expert human designer could come up with a better design, I think giving it in the hands of the application engineers is powerful because there are more of them and they can really just experiment and see what makes sense in their case. The first question, I understood it as, is our approach really RISC-V specific? Not by design, I would say. It's just that RISC-V has all this infrastructure in place to do so. And yeah, we have been targeting RISC-V cores for now, but it could be extended to all other architectures. So there's nothing really RISC-V specific in the general idea.
Take one short question before we switch laptops here. The next class, I just say we get another round of thoughts.
Our next speaker is Rafael Babarlo from Intel. There he's the high-level synthesis architect within Intel Graphics, which is a pretty cool title, if you ask me. So they develop and deploy high-level synthesis methodologies and tools to help improve the efficiency of architects, designers, and verifiers. Please go for it, Raf.
Thank you for your time. I'm Rafael Babarlo. Most people call me Raf. I'm here to talk about our work on SEER, which is the Super Optimization Explorer using eGraphs rewriting for high-level synthesis. It's a large subject. So what we mean by high-level synthesis here, we're using high-level software programs to transform into actual ASICs. We're not targeting FPGAs. We actually want real hardware out of this. We have this high-level synthesis within graphics already. We're using eGraphs as our exploration format, and the super optimization is the work we're going to cover here today. So designing hardware is actually, like I mentioned in the lightning talk, a bit like a maze. We don't know what the optimal path of the design is. We're trying to, every optimization that we apply, right, stops another optimization from being applied. So we get this phase ordering problem. So we get this every time that you add even another line or another operation to the actual code itself, it starts exponentially increasing the amount of source space. So, and then when we start playing with software and hardware interfaces, that gets a really high multi-layer problem. So if I change my hardware programming model, I change my operations, and you can imagine the headache that we start getting into. So in order to kind of do that, ideally we'd be exporting everything at the same time and then trying to figure out what the best result is. And this is what motivated us to create SEER. So we are firing off all of the optimizations that we know into the graph, into our program, concurrently exploring everything, and then using the eGraphs to efficiently extract and explore what the answers should be. So as an example here that we're going to use a lot for it, let's try just a simple loop fusion. Right. Now we can see that the top loop And the bottom loop 0 and loop 1 use array X, right? So we could say, well, let's go fuse those two together. The problem is we don't know which way the function is actually being called. Outside optimizations outside of this function may actually dictate that you're not be able to see that you can fuse those two loops. So what you do is you can either fuse the first two loops together, fuse the bottom two loops together, but you don't, as I mentioned, is like, depending how the code gets called, a greedy optimization might actually have been done, and everything's being optimized at the same time. So what we're actually doing there, right? What we're doing harder, what do we know to apply, and what does super optimization mean? We can do control path changes, like simple loop unrolling, flattening, all that stuff. We can modify the data paths, do how we actually, depending on how you do a multiplication or like finding the first bit set, actually dictates very, very different microarchitectures with different componentry, different power, and different area constraints. Or you can do different Boolean algebra and actually get lower gate count, depending on what you want your design to be. Sometimes you want more frequent, a higher performance, higher frequency, or less power. So what we do here is that we put all of this together. We put our rewrites, they are all in there. We put them in program. We put our user requirements in there, into SEER, and then we get an optimal design out. And just as a brief introduction into eGraphs, let's just try and multiply, because this is the data structure that we actually built the tool in. Let's try and multiplying the 3 times x. Now you can write 3 times x as a multiplier. You can add x plus 2x. And so when we express that into an eGraph, we put this, we can write it like this, which is kind of hard to see at first, but effectively, these are what we call E-classes or equivalence classes. So at these nodes, all these objects are equivalently the same. And if you traverse down on the nodes, you start being able to construct the same operation together. This helps us kind of start annotating what we can do to the graph. And the same way, and further explaining that, you can also write 3x as that. So the way that SEER works is that we have a C++ system C front end. In this case, we use Polygeist. We actually create just a very small IR to allow us to interface between MLIR and eGraphs. Now we use the eGraphs are good framework from the University of Washington, which is written in Rust. So we kind of needed something just to glue the C++ MLIR framework with the Rust-based stuff. And it's just as part of the experiment to make sure that we're getting in there. So as we're we extract the code, we put it into Saarland, we add it to the eGraph, and the first thing we try to do is like, okay, let's try a transformation on it. What can we apply to our eGraph? So what we're also trying to do is actually use all the MLIR transformations by themselves. So we're trying to reuse all of the LMIR framework transformations that have all of that stuff intact. We just want to extract something in our graph, ask MLIR for an answer, put it back the answer into the eGraph and continue exploring. So going back to our original loop example, we first in this here, that on the bottom left over there is how we express this in Saarland. We have a small sequence for loop 0, and inside loop 0, after that, we have another sequence for loop 1 and loop 2. So it kind of looks like this when we add it to an eGraph, and this is our equivalence classes. So we have a block, a sequence, a first loop, as another sequence, and our 2 loops. So let's go try and doing a loop fusion example. And the way we write the loop fusion rules is like this. We have a sequence. If you see in a sequence 2 loops, you can fuse them together if the MLIR transformation is a success. So we start trying to find a pattern. We translate it to MLIR. We then fuse the 2 loops together through the ML fusion loop pass. And then we create a new node for the eGraph saying that you can have a sequence, and now we loop together loop 1 and loop 2. And then we start reuniting this up and we put it back. And we now say in that eGraph, that sequence and that fused loop together are actually equivalent, the same. And the other thing that we have to do, because we're a hardware company, we have to formally verify all of our designs before tape out. We cannot tape out without saying that we actually did the correct transformations in there. And for SEER, we actually have a system C backend where we can transform SEER land into system C to put it into a formal verification tool to make sure that those two are identically formally equivalent. This is just a quick, and this is how we kind of prove that every transformation that we're doing, that we're getting back off MLIR is actually correct. So what happens once we do all of those transformations, right? We're on this extraction formula, and which is a part of that, something that you plug into the Eyck framework so that you can go, right, what is the best path that gives me the best area and power, or area and speed and performance? So depending on what you put in there is like, for our objectives, for our work, we just said, we want the max performance for the compose path with the minimal area. So another thing that we found with SEER as well, because we can do all of those interpretations, it kind of helps improve the code interpretation slightly. Like I mentioned before, you can kind of multiply by 3 different ways. In the example here is like x times 3, and I also have the I shifted left by 1 plus 1, that's also times 3. But most compilers don't understand that. So they like to see that affine thing of a constant times a variable plus another constant. So when you run most compilers, they will either loop the top, fuse the top loop, fuse the bottom loop, and this is what we kind of, based upon the work that we did, this is the baseline comparison against the tool, the commercial tool that we're using. So just by doing one of those 2 transformations, we are getting 1.3 times the area, but we're getting about 30% better speed up. But we're also producing decimal powers. But we can do better than that because we know that we can multiply by 3 multiple times in different ways. So what we do with SEER is that we see that we'll do a data path rewrite because we know of the equivalent passes to push it back to that shift by in there, and that shift going in there, adding together, we can transform that, and all of a sudden the loop fusion process can say, hey, I can actually fuse all 3 things for you instead of just 2 of them. And then once you kind of go and do a common sub-expression, elimination, kind of go, let's simplify that even further. Is that 3 times I? Okay, I'll put it back into the hardware more friendly way of doing, I shifted by 1 plus itself. And all of a sudden you have your real loop like that, and you start getting a little bit more, 50% speed up, but your power requirements actually went back to what they used to be, which is really interesting from the part of the hardware. They can say, look, I can give you more area, but I'm not going to consume any new power. And it's really, really cool to be able to do that. And the ability of doing that in a single graph and putting these things together makes it, a very, very powerful tool for ASIC design. So what do we find, right? So most of the time we can more or less match on the area on the paper. We are getting about some examples on, I think you need to check the paper, I think on an average of 3 times the power, but we blew the power budget. Now we blew the power budget because our extraction formula didn't take into account power. We just went for it and said, give me the best performance, the best throughput that you can give me with the minimal area. And that's kind of one of the lessons here that you have when it comes to those extraction formulas, you have to keep into account, power, throughput and area, otherwise you cannot go in there. So that's one of the future works of having to be more resource and area and power aware when you're doing your cost extraction. Otherwise you start getting these surprises here that you did a lot of transformations, but actually you can't ship it out because it's too power hungry. The other thing that we wanted to do is get more accurate scheduling model for the extraction, right? Depending on the different technology cells and different frequencies and things like that, you will get a different gate count, a different cell size, because you're having to drive the cells harder, and you're trying to, depending on what you do, you can't actually use certain cells because they are just too leaky. They're going to, just by turning them on, you're burning power and by doing nothing. So it varies a lot, and we have to put better costing in there to say, we can't do this because doing this implies this operator, and this operator implies this much cost, this much leakage. No, because we're going to multiply this by several times. And the last thing is better verification. We can do formal equivalence verification with this within 1 clock, but loops can describe 2 things. They can describe something that's in parallel, or they can define a state machine, right? That takes multiple clocks. And as you're doing that state multiple clocks, you can't use formal equivalence verification. You have to use formal sequential verification. That's a different kettle of fish that we haven't been able to talk. But if you change your loop, you better make sure that you're your messages are coming out in the same order, otherwise you're going to get upset very, very quickly. And with that, thank you for your time. Open for questions.
So I'm wondering how scalable is your approach? So based on my these different roughly work
So yeah, scalability is a problem. I was talking to Zach Tatlog, and don't think him. So the scalability extraction is a problem with big graphs. So depending how big it is, it takes a long time to extract. We've been the kind of problems that are operators and simple functions. So we haven't been hit by it, but as we start putting that into very big subsystems is a problem. We need to look at parallel ways of extracting with that, and we're trying to kind of find people to say, how do we extract things very well? But yes, scalability is a problem that we haven't solved it. Sorry. Yeah.
Gus Smith, University of Washington.
Mm.
Thanks for the talk. Just a quick question. Were you just using like the default bottom-up extractor, or were you doing something more complicated?
I don't know.
Maybe another way to phrase it. Do you remember how the cost model was composed?
I don't know off the top of my head. I need to ask some engineer. I have the code locally. I can look at it. I don't remember off the top of my head. I'll be very honest. But we can look at it. I can give you an answer after the talk if you need to.
Let's talk.
Cool.
One last question.
Mhm. So that tends to be a function of the cost extraction, right? So if you're trying to, the extracting, because of the extraction functions are callback, in there you can say, this is the amount of power I'm using, or this is the area I'm using, this is the kind of gates I'm using. And that's what you're doing there. It's that extraction is a problem that hasn't really been truly solved. And that's, we only kind of have simplistic things. All of our extractions have been for performance because we're in graphics and we want more power. But what we're learning from this is like, now we kind of have something that has to keep two things in mind, and we haven't solved that yet. Thank you.
Sorry to say we are having technical difficulties.
It's working, but I can't tell you, but
Does anyone have one of these? Mine isn't working for Engine. Sorry, HDMI to USB-C on the other side. Thank you, appreciate it. Sometimes these things are flaky. Awesome, thank you, if you don't mind, appreciate it. Let this be a lesson, always bring your dongles. Sorry, Engine. Exactly, thank you so much.
yes.
Meanwhile, I am delighted to introduce Sampson, who is the final year PhD student at UIUC, who works on MLAR, AI accelerators, EDA, all the good stuff that is part of the themes of this session. Go for it, Engine.
Thank you. Hello everyone. My name is Hanchen Ye, and I'm from UIUC. So today I will talk about HIDA, hierarchical data flow compiler for high-level synthesis. So first I will introduce the background, like what is data flow architecture and why we should use the flow architecture. So basically, data flow means we are instantiating a separate processing element for each task in your workload and execute them in a pipeline manner on chip, so that we will be able to pass the partial result, like the intermediate result in between the task on chip, instead of frequently swapping out the result to experimentally and swap it back for the next task. For doing that, we will need to first tile the task into small chunks, and then only pass the partial result between those tasks and overlap the execution of these tasks so that we can, in this example, we actually can tile the original intermediate result into 4 tiles and pass them one by one, right? So that we can keep the intermediate result on chip to reduce the external memory access. And meanwhile, by overlapping the task execution, we can not only reduce the latency and also reduce the on-chip memory utilization. And actually, we did a profiling on LENet accelerator on FPGA, and we can show that data flow architecture can outperform non-data flow architecture by a large margin. However, we can also observe that some data flow design point is performing worse than a non-data flow design. That means data flow actually cannot guarantee a good trade-off. So because the data flow design space is so large, making it super difficult for human designer to comprehend what is the best design choice. So actually we find the automated tool will be able to outperform the expert design and meanwhile reach that performance in a much short period of time. So essentially why designing data flow architecture is so hard, right? So we observe the 2 main reasons. The first one is data flow architecture actually demands 2 distinct levels of data flow optimization. The first one is the multi-level, the high-level data flow optimizations like the regular tensor linear algebra optimizations, tiling, fusion, permutation, packing, etc. And also we want to reduce the full tensor to partial tensor so that we can pass the partial result on chip. And meanwhile, we have the task manipulation, like where to place the task, how to schedule in the task, etc. And on the other end, we have those low-level data flow optimizations, like how do we implement the ping-pong buffer, how do we implement the stream channel, and how do we optimize each single task, like pipelining, vectorization, etc. And meanwhile, if we are targeting different backend, how to apply those backend-specific optimizations. And these 2 levels of optimization are distinct abstraction level and super difficult to be applied at a single representation. And the second observation is for data flow design, actually we have very severe, inter-kernel correlation between the data flow tasks. In this example, let's say we have 3 nodes or 3 tasks, 0, 1, and 2, right? And we can observe that the node 0 are actually sharing a same buffer with node 2. That means the implementation of array A or buffer A actually is correlated to both the implementation of node 0 and node 2. That means we cannot optimize node 0 and node 2 separately. If we do so, it will typically lead to the poor global performance. And meanwhile, because eventually we want to parallelize the execution of this 3 nodes in a pipeline manner, so we want to make sure the latency of each node is similar to each other to balance the whole pipeline execution. To do that, we need to be very carefully when we do the parallelization. So for these 2 factors, we are calling them the connectedness and intensity. So we do need to consider these 2 factors in the data flow architecture design to make it efficient. So based on these 2 observations, we propose the HIDA framework, which is hierarchical data flow representation and optimization. So as an overview, the HIDA framework will take PyTorch or CPAPAS as input. Specifically, we're using TorchMR and Polyguide as the front end. And after the compilation, in our framework, it will generate optimize the HL CPAPAS code, and we can pass it to the vendor HL tools to generate RTL. And for the whole compiler, we implemented it in the MR, including the IR optimization and code generation. So here, for the functional data flow, it is supposed to capture the high-level characteristics of the data flow. So here we introduce a hierarchical structure. For example, in this case, we have a global task graph, and let's say task 6 is a convolution layer. And inside of this small task 6, we have another sub data flow graph, which contains the tile load, tile computation, and tile store. With such a hierarchical data flow structure, we'll be able to generate very fine-grained data flow architecture to pipeline all of these components. And meanwhile, by design, the task representation in the function data flow is transparent from both, which means all the tasks are sharing the same global context, so that we can easily manipulate the task, like grouping them into some groups. Some of them will be executed on CPU, some of them will be executed on FPGA, etc. And on the other hand, after we finish the optimization at the functional level, we lower it down to the structure level, and we will have more microarchitecture details there. For example, how are we going to implement the buffers, the FIFOs, and also for this representation, all the tasks or nodes in the structured data flow are isolated from both, so that we can decouple the internode and the intranode data flow optimizations at this level. So overall, we have around 60 passes in the whole compiler. So I will not introduce them one by one, but here I will introduce two optimizations that we found are important to enable the data flow execution. So the first one is the multiple producer elimination. So in this case, the single arrows means a write operation, and the double arrows means both read and write operation. So here we can find node 1, node 2 actually both have read and write effects on the buffer 2. That means we will not be able to directly apply pipelining on these three nodes, otherwise it will cause data conflicts, right? So our approach is like we duplicate buffer 2 into two buffers, buffer 2 and buffer 2 prime. So both node 1, node 2 will have their own buffer to write and read from. But this is the case when the buffer is inside of the context, which means the only two nodes that have effects on the buffer is node 1, node 2, right? But in the other case, right, let's say buffer 2 is outside of the context, which means there may have another node that having context effects on buffer 2 as well. In this case, we will merge node 1 and node 2 into a single node and parallelize the execution of node 0 and the merged node in this case. And the second optimization is data path balancing, because eventually we want to pipeline the execution of all the nodes in the graph. But in this case, let's say we are having a ping pong buffer in between nodes, all of these nodes, right? Then node 0 is writing to both buffer 0 and buffer 3, but on these two different paths, they have different number of nodes on it. That means the execution rate of these two paths are different, which will stall your pipeline or make your pipeline super inefficient, right? So our approach, the first one is we can do on-chip balancing, which means we insert additional buffers to make sure the additional frame of data can be buffered on chip, right? But if we decided to balance the buffer in the external memory, then we will instantiate a soft FIFO in the external memory and also a token FIFO in the on-chip to maintain the original dependency of the data flow. So this is the two optimizations we introduced. And then I will talk about the design space exploration on top of the two levels of optimizations. Specifically, as I mentioned, this is still the same example in the motivation section, right? So these nodes are actually having correlation with each other. So how do we deal with it? So we propose a three-step approach. The first step, we analyze the connectedness between all of these nodes. We use two maps, permutation map and the scaling map, to record the correlation between the loops inside of this node. For example, here, the first node has a relationship with the third node, right? So specifically, the first loop of the node 0 has correlation with the first loop of node 2. So we record this correlation into the permutation map, and also we record the stride relationship into the scaling map. And those analyses are based on Oppermann or linear algebra analysis. And after we have the connectedness analyzed, then we sort the node based on the number of connections and also its intensity. So intensity here means the number of operations, right? So we first sort them in a descending order of connectedness, because higher connectedness node typically will have effect on more nodes. And also higher intensity nodes are more computational complex, being more sensitive to optimization. So in this case, we will first parallelize or explore the design space of node 2 and then node 0 and then node 1. For node 2, we do not have any constraints, right? It's the first node to be explored. So if the overall parallel factor is 32, we will explore such a design space until the overall parallel factor reach 32. In this case, the final result is 481, right? But for node 0, because it has a correlation with node 2, so we need to be careful when parallelize node 0 to make sure the IO factor of node 0 is not mutually indivisible with the constraints conducted from the inferenced from the parallel factor of node 2. Eventually, the solution of node 0 is 4 and 1. And similarly, for node 1, we apply a similar approach to generate the IO factor of node 1 as 1 and 2. So with that, we can actually found with the intensity aware IA and the connectedness aware CA, DSE, our approach can generate much less bank of memories compared to the naive local DSE, even for this simple example. And for the experiments, we did an ablation study on ResNet 18, and we found that the IA and CA approach can directly determine whether the solution can scale. In this case, if we do not enable IA and CA, the solution will not be able to scale after we have a parallel factor larger than 64. And even all the solution can scale, we can still observe the IA plus CA method can reduce the memory and the computation resource utilization. And finally, we have results on C++ kernels. We compared with scale shells with also our previous work, which can do single kernel optimization very well, but it's not aware of data flow architecture. And meanwhile, we achieve even better results compared to scale shells and also to RTL, DN accelerator, DN builder by our own throughput. That's my talk. Thanks.
Any questions for Ritter? Optimizations that involved, like one of the optimizations that involved duplicating buffers. I'm just curious how you know that that is consistent. That's like maybe you have one buffer and I got two buffers. How do you go to like breaks one are they seen the three together?
So your question is how do we determine how to implement the buffers or?
Yeah, to keep the access consistent between two tasks at the same buffer.
Oh, actually, oh, yes. So we have, because if in the context of data flow, right, we need to ensure the single producer, single consumer, rule, or we cannot violate that rule. So we will do analysis to make sure all the nodes that is going to be data flowed, writing. Let's take it this way. Like every buffer is only written by a single producer and only read by a single consumer. If that's not the case, then we will duplicate those buffers to make sure we can fulfill that rule, right? And also that's for ping pong buffers. And if it's streaming, it's slightly easier because we can easily analyze. Okay, I have a streaming channel. I just need to make sure I have a fork to fork a single FIFO into multiple FIFOs to feed the data into multiple consumers. Right.
Thank you. Again.
Thank you.
This is a great session. Thank you for coming and enjoy lunch, which is now. Let's